Chapter 6 section is called LHospitals Rule. And LHospitals Rule is used to find limits that we otherwise would not be able to find. I guess we talked about how to handle limits that are 0 over 0 back in Chapter 1. But L'Hopital is going to streamline that process. What if we have a limit that it results in infinity over infinity, or really close to 0 times some really huge number? What's the result of that? Because remember, we're only getting close to 0, and we're getting really huge in all of these cases. And so what is that ratio? Well, L'Hopital was a mathematician who said, you know, if we're taking a limit and it results in one of these three scenarios, here's what we ought to do. First of all, let's call the function a rational function. Let's make it a fraction. And this limit, which is really difficult to determine because it results in one of these three scenarios up here, that limit can actually be found if you just take the same limit, but take the derivative of the numerator and the derivative of the denominator. We're not talking about a quotient rule here, but just derivative of the top divided by derivative of the bottom. And there are three indeterminate cases, as we've mentioned up here: 0 over 0, infinity over infinity, 0 times infinity. And let's treat each one of those individually. So, indeterminate case 0 over 0. We cannot determine exactly what that ratio is. If I were to put a 0 in for x, I would get 0 over 0. So let's try L'Hopital's rule. Let's take the limit as x approaches 0. Nice rational function was given to us. Derivative of the top, secant squared, divided by derivative of the bottom. And now what is the secant of 0? Well, secant is 1 over cosine, or reciprocal of cosine. Cosine of 0 is 1, so its reciprocal is 1. 1 squared is 1. We're going to get 1 over 1. And so when we had really close to 0 divided by really close to 0, couldn't determine what it was. No, it comes out to be 1. If I were to put a 1 in for x and put a 1 in for x, 0 squared over 0. Okay. Again, only really close to 0. So I'm going to have to chain rule the top. We're going to take the limit as x approaches 1. 2 natural log of x to the first times 1 over x over 2x. Well, now let's see. That is 2 natural logs of x over 2x squared. 2's are going to cancel out. And the natural log of 1 is really close to 0. And let's see, I guess technically we should have, well, no, we were okay. We were okay, no technically about it. And if we were to put a 1 on the bottom, so I think for that one, we're actually going to get 0. And whether we were approaching 1 from the left or 1 from the right, the natural log whether I'm approaching from this side or from this side. Either way, I'm getting really close to 0 on top, and I'm getting a 1 on the bottom. So I think we're getting 0 for that one. So that's how we're going to handle that indeterminate case 0 over 0. Now, what if we can't determine the limit because it's some really big number over some really big number? And if they're the same, well, I guess you get 1, but if they're not the same, well, what do you get? If I were to put infinity in place of these x's, I'm getting huge over huge. Limit as x approaches infinity. Derivative of e to the something is e to the something times the derivative of the something, 5x squared. Let's see, I'm going to get 10x. Now, if I were to resolve this thing right here, I think that results in a 5 on the bottom. The x's are going to factor out to be a 1. And we have e to the x squared on top, 5 on the bottom. If I put infinity in here, I got huge divided by 5. 1/5 of a huge number is also huge. How about this guy? Natural log of a huge number is huge. Cube root of a huge number is huge. So I can't determine exactly what that is. So I'm going to try L'Hopital. Derivative of the top, let's see. Derivative of natural log is derivative of the something divided by the something. Divided by derivative of the bottom, and I will think of this as 2x minus 1 to the 1/3 power. I think I'm going to get 1/3 2x minus 1 to the negative 2/3. And then I'd have to multiply by the derivative of what's inside, which is 2. Well, I guess I can multiply this 2 by this 1 and call this a 2. And I think what I'm going to do is take this guy right here, this 2x minus 1 to the negative 2/3. I think I'm going to write that on the bottom. Call it 2x minus 1 to the 2/3. All right. Now, it's a fraction with 4 levels. Instead of dividing, I'm going to multiply by the reciprocal. 2x minus 1 to the 2/3 over 2. 2's are going to cancel. And this 2x minus 1, I've got on both top and bottom. Now when it's on the bottom, it's got to the 1st power. I think what we've got here is we're going to be taking the limit as x approaches infinity. I think we're going to end up with a 3 on the top. And I think we're going to have a 2x minus 1 to just the 1/3 power on the bottom when we resolve these exponents. And now when I put this huge number in for x, I get a huge number on the bottom. And 3 divided by huge gets pretty darn close to 0. Indeterminate case 3. This is a real tug of war between really, really small times really, really big. Where does it end up? Well, according to L'Hopital, we've got to have a rational function. So we've got to somehow turn this into a fraction. How do I turn this into a fraction? The first job would be to rewrite this so it is in fractional form. Limit as x approaches 0 from the right, because we're dealing with natural log. How about if we keep natural log right here? But how can I put this to the bottom? Well, if I move it to the bottom, you would have a negative exponent. Now, if I put a 0 in place of these x's, well, if I put a 0 in here, I would have gotten 0 times negative infinity-ish. And so that's why I've got a L'Hopital situation. So now I'm going to resolve this using L'Hopital. Limit as x approaches 0 from the right side. Let's take the derivative of the top, divided by derivative of the bottom. Well, like we did in that previous problem, let's not write this as x to the negative 3. Let's call this negative 2 over x to the third. And just like in the last problem again, I'm not dividing by that. I'm going to multiply by the reciprocal. I'm going to multiply by x to the third over negative 2. Don't divide by a fraction, multiply by the reciprocal. I am taking the limit as x approaches 0 from the positive side. And it looks like when I resolve the x's, I'm going to get an x squared on top. And putting a very small positive number in here, I'm going to get 0-ish over negative 2-ish. I'm going to really get close to 0. So the biggest adventure is how do you turn a product into a rational function? A little bit easier down here. If I put infinity in here, I've got huge times really close to 0. E to the negative huge, really close to 0. But since this has a negative exponent, it could naturally go down to the bottom. I think to rewrite this problem as a rational, I'm going to have 4x squared over e to the 2x. And now it's L'Hopital time. I'll take the limit as x approaches infinity, and I'll get 8x as the derivative of the top, and derivative of e to the something is e to the something times the derivative of the something. And even though I could do something with that 8 and the 2, I'm still going to have a really huge number divided by a really huge number. And that means L'Hopital, and so I'm going to have to L'Hopital a second time, and we'll see that numerous times. That's something that we'd see on the AP exam, any kind of an assessment that I give you. Sometimes a L'Hopital problem involves 2 or 3 L'Hopitals before we can resolve it. Derivative of the top. Derivative of the bottom. Well, let's see, 2 comes along for the ride. Derivative of e to the something is e to the something times the derivative of the something. And putting a huge number down here, I'm going to get 8 divided by huge. Going to get pretty close to 0. So be ready to handle any of these 3 indeterminate cases by using L'Hopital's rule.